Hey everybody, this is Larry. This is day 26 of the April Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Min cost to connect all points. Happy Tuesday, Monday, wherever you are. Hope y'all have a great rest of the week, by the way, and had a great weekend. Alright, so let's get started. My neck is a little bit better today, by the way. I guess I lied about let's get started. So yeah, so we'll see how that goes. But okay, let's actually get started. I don't know. Cool. Okay. Integer 2D plane points XY. Okay, the Manhattan distance. Return the minimum cost to make all points connected. All points are connected if there's exactly one simple path between 2 points. Okay, they connect in a weird way. Or maybe that's not weird, but it is just a little strange. I have to think about. I think the thing I would say is. I think I'm trying to figure out a little bit of. I'm trying to understand this problem in the sense that, let's say, let me see if I can draw it. Hang on. I think I'm just trying to think through what this problem means a little bit. And what I mean by that is that, for example, let's say we have this image, right? This image that they give you. Can I resize it? Nope. Okay, fine. But I think what I was curious was whether like is it possible to connect it like this? Someone like that, or and even drawing this is a little bit awkward because the connecting is Manhattan distance. So I feel like it's more natural to draw it like Manhattan distant-y. And in that case, there's something like this. Does this kind of 2 line? Do we connect here? So I guess those are the questions I'm thinking about really quickly. Doesn't seem like that's the case though. So yeah, I think in general, let's say we don't know anything else about this problem, or like knowing Manhattan distance for now, the intuition is that the minimum cost to have all points connected is with one simple path is a minimum spanning tree. And minimum spanning tree, maybe that's the theme of this week, I don't know. A minimum spanning tree is easy to do. The core part about minimum spanning tree is that it is a greedy solution. You can read more about it, and there are a couple of possible solutions in a sense, or like a couple of possible ways to write it. There's prims, there's cusco's algorithm, and there's also like a one that's like hybrid. I forgot the name of it off my head actually. And whichever you want to do, it's fine. So let's look at the constraints to kind of see which way we can go. I think the thing that I was hesitant for a second, well, one is what I just drew, right? I wasn't sure because when they draw it out on a 2D grid like this, it's not 100% clear to me. Seems like it's okay though. And the second thing that I was thinking of is, okay, it is Manhattan distance, right? I wondered because, yeah, I mean, I don't think it matters, but I was just thinking that, it doesn't matter in the sense that I think the greediness that allow us to solve it on in the general case also allow us to solve it for Manhattan distance. But I was also wondering, okay, it is Manhattan distance. Is there something that we can exploit to make it go faster, right? Or like better, or however you want to say. But yeah, but that being said, I don't think I have. Yeah, I think I'm just gonna plug it into. I think I'm just gonna plug it into a whatchamacallit, spanning, a minimum spanning tree algorithm. I think that's gonna. I think I'm gonna give it a try. I think that should be good. I don't think that there's anything weird about this. Yeah. And I'm not gonna. I'm trying to think because I definitely have done this explanation in the past. The idea behind union find. I am gonna use this algorithm. I think I spelled it correctly. Hopefully I did. I'm just googling to make sure that I spelled it correctly. Yeah. So this is the algorithm that I'm going to implement, and it requires something called a union find. Maybe I'll do a video about it in the future, but the idea behind union find is just that it, or sometimes we know referred to as DSU, or disjoint set union. Yeah, maybe that's it. Okay, but it supports two functions, right? Union and find in relatively efficient ways. And the way that I'm going to write it here is maybe, you can definitely observe it. Even union find, there's a lot of different optimizations that you can do. There's, for example, just a naive union find, and then there's also what's it called? There's path compression. There's also I forget what is it? Something like union by rank, or by size, or by depth. There's so there are a couple of optimizations you can do. And what I was gonna say. Oh yeah, and the optimizations you do will have different different complexity impact is what I was looking for. So definitely check those out. I'm going to do it my way in that this is usually good enough for me. But that said, what's usually good enough for me may not be the case in certain even competitive contests, because if you allow someone to for example, in certain contests they have this challenge phase or hacking phase or whatever. If you allow that, then maybe it's not as good, because there may be some edge cases. But I find that for random-ish inputs is fine. I do path compression, but I don't do the union by rank thing, mostly because I'm lazy. And yeah. So there are a couple of ways you can do it. Yeah. So yeah, so let's get started. N is equal to the number of points, and there are a couple of ways you can do the union find. I'm just going to make it into an array. So you could, the way that I think about it is the union find is basically it starts out. It doesn't have to be, I guess, technically, but it starts out as n different trees, each one with it's a rooted tree, right? And then as you combine two of them, you basically combine the trees into one same group. And there are ways to kind of make the tree a little tidy, if you will. But the invariant there is that the root of the tree, the root of the, or a node, or the root of a node will define everything that is inside that tree, or that the same equivalence set, as they would say. So yeah, so that's how I usually start it. And here I go x for x in range of n. Make this a list. Basically, it is the invariant here is that it is pointing to itself as the root of that tree. Is basically the idea that I have. I call this union. It's just historic reason. And I also have uFind just for historical reasons, because when I used to write this, like way back when, I think find and union, maybe depending on the language, is sometimes a keyword. So this is just like a habit thing. I don't know if I don't know. I don't know if I recommend it. But yeah, so if parents of x is not x, that means that if x is not the root of itself, find the root, right? So parents of x is equal to uFind of parents of x. So this is recursive. And the reason why I have this, so if you don't update it, you could also just do like return this way. But the reason why we're able to do this is almost like memorization. And because you memorize it, so then the next time you call this, you don't have to go through the entire linked list or up the tree, if you will. It becomes almost like a sort of memorization, if you will, except for that memorization you update it, often because depends on how often you compress, right? And then at the very end, you return reruns of x. So that's the way that I usually write it. And the way that I write union is I have two sets, right? So yeah, so I have the set A, I have set B, and then I just combine parents of UA is equal to UB. So basically, I mean, it doesn't really matter which way you go because I am lazy. You can, depending on how you want to do it. So the right way to do it with union by rank or size or depth is that you keep track of keep track of the other thing, and then you do like an if statement if some f of UA is bigger than f of UB or smaller, depending on how you want to write it. Then you have this, else you basically you try to determine which one becomes the root of the other. But for me, I do it this way. And if I really worry about being challenged and I'm still lazy, I would do something like if, I mean, this isn't quite Python, but I do something like if, basically flip a coin, right? And then I do something like that. So it's really hard to challenge, and probabilistically it'll be okay if you do enough unions. And the idea here, but it's also, I find that, and this is just from experience, from competitive, this is usually okay. But that said, for interviewing, it is a little bit less okay because you have to explain it. So be sure that you know the other one. But basically, make all the children of UA UB, or point to root of UB. That's basically the idea here. Yeah. And then now there are a couple of ways you can, with union find, it's a little bit easier in that it is the way, depending on how you want to write it, it's going to be y log e. You can, for cusco, I guess technically if you really want to think about it, prim is going to be v or y log v for prims. Is it? Let's see. For each node, I think it depends on how you write it as well, because it depends on the heap implementation, which there are some nuances in actual thing. And also log e is going to be log v anyway times 2 for, you know, for reasons. But is it though? For each v, we sort all the other v's, but I think it becomes v log v plus e or something for prims. I actually don't remember, so definitely leave it in the comment below. I think that is roughly right, maybe. And that's assuming that you have an update heap thing. But that said, keeping in mind that this is the cusco's bit, and this is something that you can just look up in a textbook. I'm a little bit weaker today. Maybe I do need to review it at a certain point. But keeping in mind that y is at most v squared, so that y is equal to, or this other thing means y log e is equal to y of log v squared, which is of course equal to 2y log v, which, you know, if you give it a big O, you could just remove it, right? So yeah. Anyway, we can do all the complexity later. And that assumes, of course, this is O of 1, which, yeah. But all right, let's get started though, which is, depending on who you talk to. I know that some people are really, really pedantic about it. If you do it correctly with union by rank, it's going to be the inverse Ackermann function, sometimes written as alpha to the -1 or alpha prime or whatever, right? I get it. But that number is like 5 or 6 to the number of atoms in the universe, so it's effectively constant, really. But some people really like to be picky about it. I don't know. It's fine either way, if you ask me, for any real numbers of n, because for any bigger numbers of, I mean, it just grows very slowly. Well, Ackermann function grows really fast, and an inverse Ackermann function grows really slowly. Okay. So then what's left to do for cusco? And this is, so I actually, so the reason why I like these minimum spanning tree algorithms, I don't think I have done one on video in a while, so maybe I'm a little bit slower today. So if you're really fast, props to you. But it is greedy, right? And greedy means that you can, and you know, there's proofs and stuff like that, definitely. read that up. But it also means that yeah, what I have to do is take all the edges and then sort them, and then I'll be super happy, and then just add them one by one if they're in the same thing. So let's try that. So yeah, so edges is equal to so then now we have for, and of course the other thing you should do is make sure that it fits in. We have 1,000 points. To be honest, E log E is probably a little bit tight because E is going to be n square in this case. You can maybe do some maths to kind of just look at to change that a little bit, maybe to filter it out. But I don't know if that works actually. But either way, that means that this is going to be 1 million. Log E is going to be 10. So 10 million in Python is always a little bit scary. So we'll see how that goes. But let's play around and see if this works. And also, I guess technically we can make this choose 2 real quick, so that you basically get rid of half of them. So then now instead it's only 5 million times, or 500,000 or something, times 10. So maybe that'll be faster. We'll see. But yeah, edges, we just literally create all the edge lists. Yeah. So we have basically we have ij to remember, but also the sort key, which in tuple language is point sub I. I know what you're thinking, of course, and I'm thinking it too. Is that why don't we have a helper function about this? And that's what we should do, to be honest. But I am doing a little bit of a premature optimization, but this is almost like a Leetcode specific optimization, because I definitely would not do this if I was in an interview or maybe even in other languages. But it's just that if I'm doing 500,000 function calls, it actually slows down a lot. I don't know, this is definitely maybe sketchy even for Leetcode, but I just feel like sometimes I do these optimizations because Leetcode is sad. So yeah, so then now we do a sort, and then we just can go by the thing. So we in edges, right? Yeah, so total is equal to 0. This is just the total cost, and we could even add edges. Oh, we already did that. So left is equal to n minus 1. Basically, we know that we want a minimum spanning tree, and of course, a tree by definition with n nodes is going to have n minus 1 edges. This way, we can early terminate. Is why I have that. I wonder if you could do some. Yeah, okay, but yeah. Oops. And now this is basically if union finder this is not equal. Basically, if they're not the same, then we do want to union them. And in that case, we add the cost. Again, premature optimization may cost me. I don't even know if this is necessary, but you can say that Leetcode, I've lost a lot of faith in Leetcode, clearly. Otherwise, I probably would just make it cleaner. I don't know. I don't know if I feel great about that. But anyway, if left is equals to 0, we break. And then we turn total. Because this is a full graph, this should always hit, and we should always terminate early. So there shouldn't be any error cases because we have a full graph. Unless I have a typo or something, obviously. But let's give it some minutes, see if it's fast enough. Apparently I did last time, it's 4 seconds almost. Okay, wow, this time is much faster, so I'm happy about that. I actually don't know what I did last time, so we'll see together. But yeah, like I said, so this is going to be y log y, like we said, and this is just going to be O of y times, this the cost of U find and U union perhaps, and of course you can look that up. I consider it constant relatively, or maybe log star n if you want to look up what log star means. The iterative logarithm, in case you want to iterated, I think. I actually don't remember, iterated logarithm or iterative logarithm, I don't know. But yeah, that's basically all I have for this one. Let me know what you think. I know this is a longer video because I've been talking a lot. I haven't done a minimum spanning tree problem in a long time, especially for daily problems, so that's why maybe. But yeah, what did I do? Oh, I did the same thing last time, actually. And so that's actually pretty interesting, right? So I did literally, wow, this code is actually remarkably the same. But so why is it 2 times faster? It's 2 times faster because this time, and I called it out a little bit, I have this left function so that I could terminate early, and that made it a lot faster. Because otherwise, actually, everything else is more or less the same. I mean, I have some variable names different. I actually did have a helper function, so maybe the helper function would have been okay. So I'm a little bit... Also, I am a little bit dumb because I did this thing again, but I forgot that we actually have this here, which I didn't do last time. So you can actually simplify to this, and obviously it'll be okay because we already did this calculation. I was wondering about... I thought that felt repetitive when I was writing about it, I forgot, and I was focusing on the left. So yeah, cool. So yeah, so you know, this if statement, and of course this and this, keeping track of left made this more than twice as fast. So definitely do stuff like this if you want, I guess. But you know, it's it should be okay. Anyway, that's all I have for this one. Let me know what you think. This is a little bit verbose because I wrote a lot, but I think the core part of the code is not that much. So let me know what you think. Stay good, stay healthy, to good mental health. I'll see you later and take care. Bye bye.